Okay. All right. So I guess I've been asked to start over because everything was totally screwed up. All right. So it's never a good sign when you're a computational astrophysicist and like all your technology breaks. So I'm going to give a talk about general relativistic hydrodynamics on the moving mesh. This is work I've been doing with Zach Etienne at West Virginia University for the past 2.5 years, actually. All right, so I'm going to start with a brief outline. I'm going to talk about numerical simulations of astrophysical phenomenon and the different methods that we use to attack it. Namely, the three methods fall under three ways of viewing the equations: Eulerian schemes, Lagrangian or SPH schemes, and arbitrary Lagrangian Eulerian schemes. And then I'll briefly talk about the L scheme Manga, or moving mesh scheme Manga, which is built upon the SPH code Changa. And then I'm going to talk a little about general relativistic hydrodynamics on the moving mesh and give my conclusions afterwards. And this work, basically, which I'm going to talk about today, mainly appears in the paper denoted in red, Chang Etienne 2020. All right, so let's start with numerical simulations of astrophysical phenomena. So basically, what we're trying to do is we're solving the Euler equations, right? The Euler equations written here is equation of continuity, equation of momentum, and not written here is equation of energy. And there are two ways of viewing these equations, right? So you're looking at fluid flow in the universe, and one way of doing it is you discretize the universe, and you ask what's flowing into every discrete cell and what's flowing out of every discrete cell, right? And this way you're tracking the fluid flow on some kind of fixed mesh usually, and this is what's called the Eulerian picture of it. So this is basically the left-hand side of that middle equation here is partial derivative with respect to time plus some effective term. The other way of doing it is that you track each individual fluid element, right? And each individual fluid element just follows the Newton's second law, F equals ma. And so basically you just look at basically how the fluid quantity changed as total derivative with respect to time. That's the Lagrangian picture. Now, the Lagrangian picture is used very widely in astrophysics, mainly for galaxy formation, right? And basically what you want to do is you want to model the fluid as a number of discrete particles, and you subject this discrete particles F equals ma forcing. Now, the challenge there is that in a fluid, the forces are usually things that depend on continuum values, like density or temperature or whatnot, right? And so you need a way of basically moving from knowing having a bunch of discrete particles to an estimate for continuum values, right? And that's done very similar to basically like the US Census or whatnot, right? What you do is you take an estimate over some fixed region, right? And in this case, the density estimate is provided by doing a weighted count over a certain volume that includes the nth nearest neighbors, where n is usually a number like 64, right? So basically, you just count the nearest 64 neighbors, you see how big the kernel was in order to basically account for that, and then you have your density estimate in that case. Now, the main computational challenge is doing rapid search for the nearest n neighbors, but basically we've figured out how to do that over the past few years, namely because of gravity codes and stuff. And so these map very well to basically n-body tree codes. The other way of looking at this is the Eulerian scheme, which is basically how everyone in GRMHT basically solves the equation, right? You write them down as a grid, as a flux conservative equation, as basically some derivative of some conserved quantity is equal to some divergence of some flux plus some source term, all right? And basically you solve using some finite volume scheme typically, right? You basically stuff comes in, stuff comes out, right? And basically the total conserved quantity in that thing is basically the difference between stuff coming in and stuff coming out, and basically whatever source terms you have in there as well, okay? Now, there's a third way of looking at this, right? Which is also pretty old, which is called the arbitrary Lagrangian Eulerian scheme, right? And in that case, what you do is you move your mesh cells arbitrarily, right? And usually you want to take a choice of the velocity such that it makes sense for it. So usually that choice is something like the local flow velocity, right? So another way of thinking about this is that you're looking at basically how a cell changes as it moves with some arbitrary velocity w, right? And so basically that's d by dt in this W reference frame, and then you modify your vective term that way as well, right? Now, this is used widely in continuum mechanics, right? So basically this top thing is a steel blade cutting into a piece of steel and basically blading it off, right? And so in that case, you can see like the meshes can be unstructured, you have strange arbitrary boundaries, right? And so this stuff tends to be very, very useful for fluid-solid interactions. And if you have, if your flow velocity is far larger than sound speed, in principle, you can also have like dramatic improvements in basically the speed of these codes as well, right? Now, the traditional L schemes tend to suffer from a phenomenon known as mesh distortion, right? And so what it usually requires is a remesh, which is usually a numerically diffusive action, right? So basically, this is shown in this top panel here, where you have a 3-point shock, basically a shock moving into a lighter and then a heavier fluid element. And what happens is that the shock moves more quickly through the lighter fluid, and so what happens is that the mesh will eventually start getting distorted, right? Now that's fine, the mesh gets distorted up until a point where mesh lines start crossing each other, and then you have some real problems then in that case, right? And so what needs to happen is that you tend to remesh this mesh. So that's shown in the graphic basically in the middle of the page, where basically you have something that looks like Rayleigh-Taylor instability. Basically, as the mesh deforms, eventually the mesh gets too deformed, and then what will happen is you have to relax the mesh back into something that looks much more regular. Now, these L methods were not widely used in astronomy until about 2010 or so, and the key thing was the development of basically the application of Voronoi meshes to solve this problem of remeshing. This is basically done by Springer 2010. Now, how do these Voronoi meshes work, right? So they're beautiful, basically, in the following sense, right? So a Voronoi tessellation, all right? So you have an arbitrary distribution of points, and you want to basically divide up space using this arbitrary distribution of points, right? And the way you construct a Voronoi mesh is that for every pair of points, you draw the perpendicular bisector between the two, right? And if you do this sufficiently, right, what will happen is that you get a tessellation, which is known as a Voronoi tessellation, that has 3 important properties, right? So the first important property is that they are unique. Second important property is that cells are convex, which means that every point within that cell is closest to that mesh generating point. And then thirdly, the cells deform continuously under small perturbation. So this is seen basically by this animation on the left, as this cell is, at this point, is moving across this distribution of points. Basically, all the cells deform continuously, and then cells that are far away don't basically are affected at all. So that's beautiful about this, right? Okay, and so because of this, you can basically get well-defined faces and well-defined volumes that basically change slowly. And basically what Springer showed in 2010 was that any flux conservative equation can be solved on these unstructured meshes, right? So this sort of methodology has been used in a number of codes, right? The most famous of all is Arepo, right? Springer 2010, but it's been used in other codes as well, like Rich, Tess, and now Manga as well. Okay, so let me talk a little about the pros and cons of Voronoi hydrodynamics, right? So the pros is that it has much better advection properties than linearity, because in principle, there is no advection if you do it correctly, right? They perhaps have superior conservation of linear momentum and angular momentum compared to Eulerian schemes, right? Angular momentum notably because you take away basically special directions, the grid directions in principle, in practice, right? They have superior shock capturing compared to SPH because they are actually finite volume codes which solve the Riemann problem, which is a shock problem, right? They may have better capture interface instabilities in principle, though that's debatable, right? You can do MHD in these Voronoi hydrodynamics, unlike SPH, though some people might disagree with that fact, though I would assert that is still true, right? You have continuously varying resolution. So in AMR, what you have to do is you have to split your cells into 2, and so your resolution jumps by a factor of 2 or 4. In Voronoi hydrodynamics, because the distribution of particles is continuous, you can have continuously varying resolution, which is a plus or a minus depending on how you look at it, right? And what's final is that anything solvable in Eulerian grids can map onto Voronoi methods, right? Now, the cons of these things is that they're much more complex. They encode basically all the techniques they use in SPH with all the techniques used in Eulerian with computation geometry. And so that basically gets the advantages of both schemes, but also the disadvantages of both schemes as well, right? You have to start thinking about the grid now, right? So normally you never think about the grid. You say, okay, the rectangular grid, you put AMR on it, blah, 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 whatever. Now you actually have to think about carefully how you lay down your grid and basically where you want your resolution to really be in a continuous manner, right? They are quote unquote slower. I put that in quotes because basically in principle, they're about actually maybe a factor of 2 slower than SPH, but in a lot of cases, they're actually equal in speed, right? So I put slower in quotes, right? MHD is harder to do in these things. There's no staggered constraint transfer scheme that exists in these methods yet, right? So you have divergence cleaning, right? Or you can have vector potential-based, cell-centered vector potential-based methods, right? But no staggered CT schemes like Athena exists yet for these things. And the last thing is that there's probably overkill for many problems, right? So for instance, like a disk problem, like which Athena++ solves extremely well. These kinds of methods may not be as useful in a lot of these predictive problems, right? But I would say that the advantages in advection, shock capturing, treatment interfaces, and conservation make it great for these dynamical stellar problems, like perhaps binary neutron star mergers. All right, so I'm going to talk a little about Manga now. All right, so Manga is basically Changa, but with some stuff built on top of it. It's actually a module within Changa, right? And Changa is an n-body SPH code, which stands for charm n-body gravity. Right? That's what it stands for, right? And the charm part is because it uses the charm++ programming model, all right, which is basically a framework to write highly parallel hybrid codes, right? So in principle, you can basically make them easy to write hybrid OpenMPI, OpenMP codes, right? And Changa is beautiful in that basically is because it's task-based method, it scales in pure gravity computations to up to about 500,000 cores. This is a low data now, it's on blue waters, 500,000 cores with 93% efficiency, all right? To give a note basically how structured Charm++ is, like when I first wrote Manga, I was just using the MPI stuff exclusively, and I did not realize I had a hybrid code until I realized it was just literally a command line option. So I ran it, command line option, it worked perfectly the first time, it was just very nice, okay? Now there's a few problems that can be solved in Manga now, right? So these things are a little bit messed up right now, but I apologize. So basically, I can solve hydrodynamics, okay? I have self-gravity in there, and basically, there's also stellar equation state, all right? Now, the stellar equation state is interesting. I'll basically play that once back again. This stellar equation state, if you look carefully, those are eagle eye, look carefully on the grid sizes, they're about 10 to 6 centimeters. So this is actually a nuclear equation state from stellarcollapse.org, right? That's been implemented in Manga, done both in moving mesh and in SPH, okay? There are other basically problems which we are able to do now. One problem is basically radiation hydrodynamics, and the other problem is basically radiation hydrodynamics on the left, and the other problem is basically GR hydrodynamics on the right. This is just on GR hydrodynamics, the one that what I'm showing here is a TOV star, which is just basically evolving slowly, all right? Now, for those who are basically sharp and eagle-eye, what you notice is that the radiation hydrodynamics have two crossing beams that cross each other correctly, right? And so those are basically who know anything about radiation hydrodynamics now. Now note that this is not either a flux limit diffusion scheme, and it's not N1 either. This is actually the full transport equation in Manga. Okay. Now, so there are some current features of Manga, which basically we have hydrodynamics on the moving mesh, self-gravity, entropy or energy solving, depending on which way you like to look at it. We have multi-stepping, and what that means is that each cell has its own time step which are factors of 2 over the global time step, all right? So basically it's individual time stepping, just for speed reasons. We have different equation of states in there. The Mesa equation state is the one that we use the most, but as I showed earlier, we can also use equation state from stellarclocks.org. We have what's called moving and reactive boundary conditions. So basically you can have fixed boundaries in there, right? Let's say like a ball, a solid steel ball, whatnot, in your fluid flow, and that solid steel ball will basically both react back on the fluid flow and will react to the fluid flow, right? Okay. So this is basically possibly useful in some areas of research, including envelope evolution. We have radiation hydrodynamics in there, which basically where we solve basically the flow transport equations, all right, for radiation. All right, and now we have GR hydrodynamics on the moving mesh, right? So this is basically work I've done with Zach Etienne recently. There's some near-term goals as well. Basically, hopefully we're having an open source version released basically sometime in mid-2020. I want to basically get the moving mesh GR hydro for binary neutral star mergers, and also hopefully in the not too distant future, some high order spatial reconstruction methods, and then some long-term goals as well, which I won't talk about now, right? There's some current problems which we're doing with Manga already, and these are basically either been published or about to be published. So one is basically common envelope evolution, which is something I've done with my student Logan Bruce. Basically a star two binary stars, one of which is basically a giant star, and a secondary star, which basically enters it, basically strips that envelope of that star, producing the most interesting binary systems in the universe, which are needed to basically understand like possibly LIGO sources and various other sources. And the other basically problem which we've been doing is basically tidal disruption events. Stars that move too close to a supermassive black hole get tidally disrupted, ripped apart, and basically emit lots of radiation, which is useful as probes of centers of galaxies. Okay, so I'm going to talk now to the main point, which is basically general realistic hydrodynamics on a moving mesh. All right, so basically I wrote in the very beginning, all right, and this is basically something that was talked about by Volker Springer, is that any flux conservative equation can be solved on a moving mesh, right? And so basically GR hydro can also be written as a flux conservative equation. So in the top, I've written the Euler equation as a flux conservative equation, right? But you just need to do a mapping basically to the general relativistic generalization of that to basically do it, all right? And what's very interesting about this is that basically if you write the density as rho star, okay, then the flux basically becomes rho star times V, where V is basically the grid velocity within that grid, right? And so basically everything that we've done for the moving mesh maps really well over to GR hydro as long as you rewrite your equation in this way, right? So GR hydro, right, can be solved on an unstructured moving mesh, right? Now, there's some technical improvements that were required basically to make this happen, right? A few of these basically is that one thing that was done is that we rewrote the second order integrators, all right? So a lot of second order integrators basically are derived from basically Volker Springer's original paper in 2010, where you have to write the equations in two different forms, both in conservative form and differential form, basically in order to get second order accuracy integration, right? So basically we wrote this as using something, what's called a Van Leer second order integrator, which is similar to Athena++. And what's nice about this, you just write your equation once and then you're good to go, right? We used Paul Duffel and McFadden's 2012 Riemann solver, right, which they use for tests in order to solve the things on moving faces. There are perhaps one better method than this, but we haven't basically fully debugged that method yet, right? One thing that is different about GR hydro versus basically Newtonian hydro is that mapping from conserved variables to primitive variables is non-trivial now. Basically, it requires you to solve a non-trivial expression. And so what we use is basically a thread-based version of Scott Noble's conservative primitive solver, basically which checks, which were implemented in Illinois GR NHD to ensure a reliable solution. And all the equations that we did were coded up in NeurPlus, all right, and exported to fast C code or make it work. Right. Okay, so let's basically show some of the stuff that we're able to do. So this is a TOV star model on a moving mesh, right? The star was modeled by 10 to the 6 mesh generating points, which basically means about roughly something like 120 points across the radius of the star, right? This was a fixed TOV metric because we don't have dynamical gravity yet, right? And run for about 24 dynamical times, right? And so what you see is basically a diffusion material due to sharp boundary of the surface of the star. So basically one measure of how accurate TOV solvers are generally is to look at the change in central density as a function of time, right? And so basically we have two different resolutions here, all right? We have one resolution which is, so I put n equals 2 times 10 to the 6. I said the number of mesh generating points is 10 to the 6. The other 10 to the 6 particle is actually for the atmosphere itself. So the one thing that's different about mesh methods versus SPH methods. SPH methods can deal with vacuum, mesh methods cannot. And so as a result, you have to have like a large number of particles typically for the atmosphere. Now, this does not entail a huge cost because we have individual time stepping for these things generally. And so basically they don't, most of the time they're just basically sitting out there doing nothing, right? So it's not like a big deal, right? So a high resolution I mean 10 to 6 particles, we have a drift in the central density about 2% over 24 dynamical times, right? At lower resolution, something like 10 to 5, so 10 times less in particle number, basically, or a factor of 2 in radio resolution, then basically we have much more severe things, something like 8% over 24 dynamical times. And basically, the other thing you can see is that we have a single step method and a multiple step method. This is just refers to basically whether or not you're using individual time steps or not. And basically the results are the same for individual time step, which means that individual time stepping is working perfectly well in this method. All right. Now, the reason why we're getting this, so 2% is actually is small, but it's actually pretty bad compared to basically what mesh code like Illinois GRNC is able to achieve, which is a factor of 10 less than this, right? Now, this is actually well understood, I would argue, because Duez et al. First basically studies in 2005, and basically what happens is that these sorts of things are really sensitive to spatial reconstruction, right? So what happens is that Illinois GRNC goes up to, I think, what's it like, at least third order, maybe fourth order reconstruction, all right? And so because of that, basically it's able to get the face values much more accurately. But for these unstructured moving mesh methods, only second order is possible right now, right? And so basically when you go to second order, basically Duez et al. Found basically also of order something a few percent drift basically over something like this 24 dynamical times as well, right? So this may be fixed in the near term with developments in unstructured high order methods, but as of now, this unstructured high order method is an unsolved problem in astronomy, all right? So not in other areas, okay? Now the other thing that we did is that we basically took the star and reduced the pressure by 10%, all right? And so what happens, the star starts to oscillate, okay? And so the star will oscillate radially at the fundamental mode, all right? And basically you can see basically the star oscillating at some frequency, and we can basically do a Fourier transform of the central density to see basically what that frequency is, right? And so we did this test basically in with both single time stepping and multiple time stepping, and what we found was basically, and with Illinois GRNHD, and this is basically shown in this right plot right here. You can see basically Illinois GRNHD in the dotted line has a peak at some value, and the peaks that are found in the moving mesh methods basically more or less match that. Now, there's one critical difference about Illinois GRNHD versus these methods. Right here, I am having a fixed metric, whereas Illinois GRNHD has a dynamic metric, right? So basically, these are not exactly an apples-to-apples comparison, but it's definitely encouraging because we don't expect a huge change in the metric as a function of time, right? But that remains to be seen. So the future basically, future would be incorporating a dynamical space-time solver into Manga to basically solve the full moving mesh simulations and hopefully move to basically finite neutron star merger simulation in the not too distant future, right? So let me give my conclusions now. Moving mesh methods have a number of advantages and disadvantages for astrophysics, all right? And in particular, I will argue they're particularly well suited for dynamical stellar problems. And then a number of them have been done already, including common envelope evolution and tidal disruption, right? And GR, basic hydrodynamics with static state science are now working, okay, which is actually the bulk of the problem with GR hydro, okay? So basically the next step would be including dynamical spacetimes, and that's basically work that is continuing to happen with Zach and Tien, right? And that's it for me.
Thank you, Phil. The audio worked great. Thank you to Joseph and everyone else who helped solve the problem. And let's see what we have in the way of questions. Let's see. Several questions. Okay, Vasily.
Hello, very nice talk. One thing about the TOV in your moving mesh, does the tessellation being moved in such a way that the grid lines align with the surface of the star? Because if that's the case, then you're going to have larger oscillations than in the Cartesian case, because you're actually capturing the stellar surface and atmosphere interface at all angles, and that's different to Cartesian codes where you have that least diffusive situation only on the 6 points, right? So maybe that's something to think about. So I'm not sure if that's only that's only to the spatial reconstruction. If in spherical coordinates we see the same thing basically, because I mean you're perfectly capturing the point where those codes perform worst, which is the interface of the stellar surface and the atmosphere. So Cartesian codes help you because they're more diffusive, because in almost apart from the 6 directions, which are the coordinate axes, that surface is not aligned with the grid line, so they're more diffusive and help you. So that's something to think about.
Okay, I see. They help you in what way?
That basically, so think about, I mean, in the Cartesian grid, the star will look like a Lego sphere, right?
That's right. Yep.
So, and I mean, in any apart from the 6 directions, the cell interfaces are not aligned with the surface of the star. And where they're aligned, you basically get first order reduction, because you're least diffusive in that direction, because the surface actually sits aligned with the cells. So if your tessellation actually is symmetry conforming in the sense that the tessellation picks out the surface perfectly, then you will run into the same problem as spherical coordinates, where you basically have larger oscillations due to that fact. So that's something that we saw in spherical code compared to Cartesian codes, for instance.
Right. Yeah. So there is one difference here. So like I didn't think carefully enough about how to do doing the so let me take a step back. So like I said, you have to think about the grid in this case, and of course, like I do as I say, not as I do. So what I did, right, is that basically I took a perturbed cubic approximation. So everything there is actually cubic. So it's actually closer to Cartesian. The difference, however, is that basically the mesh points are moving, all right? And so, yeah, you're going to have some diffusion across the mesh boundaries, all right? But you can have a less of an issue because there's less advection there as well, all right? So it's a plus or minus. So you're right in that basically having aligned with the surface is a little better, but we also have the additional fact that basically we are not moving much material across that surface.
Okay, thanks.
Okay, I think Ian was next.
It's a similar question related to the surface. Have you tried using the multi-material capabilities to essentially do away with the exterior atmosphere by applying an appropriate boundary condition at a conformed surface grid line?
Well, okay, so the question then would be like, what would be the appropriate boundary? So in principle, we can apply a boundary condition there, all right? but I haven't thought about basically what the right boundary condition would be in that case, actually, for the surface. I mean, ultimately, I'm not after TOV stars, right? Because ultimately, I'm after basically binary neutron star mergers or neutron star black hole mergers, where basically it's hard to define what the boundary condition should be at any particular surface or whatnot, right? So this right now is just basically a proof of principle, right? But I am curious basically what your thought would be on what an appropriate boundary condition would be at the surface of a spherical star in order to not have an atmosphere.
I'll email you a thesis.
All right.
Okay, and Beanie.
Oh, hi. Actually, Manuela had a question in chat that she couldn't raise her hand for, so perhaps she wants to go ahead.
Oh, I didn't raise my. I mean, it's interesting. It's a very beautiful formulas, by the way. Congratulations. This is really very nice. I was just wondering about the possibility of having a mixed code where you do moving meshes in hydrodynamics, but not in MHD and GR.
Okay. Right. So a few things here, right? So MHD is possible on a moving mesh, right? Because you could write it as a flux conservative equation, right? The issue with MHD, well, okay. So it depends on basically what you think a problem might be. Okay. So what we can do, right, is that we can write a vector potential formalism for it, and then solve the MHD equation just fine. Okay. The issue is that in a moving mesh, if you go from the vector potential to the B field, that involves gradients of the vector potential, and gradients of the vector gradients of anything in a moving mesh is always a problem because your grids are unstructured. Whereas basically, if you did gradients on a Cartesian mesh, it's a little easier because you have higher order basically estimations of gradients. All right, where such things do not quite exist yet on a moving mesh, right?
Right. Yeah, and that's why.
So, yeah. So I would say for the MHD part, the real challenge is not to basically write multiple methodologies for it. The real challenge is to come up with a higher order method for a moving mesh, right? And such things do exist, especially in the aerodynamics community, where they have a real need for basically unstructured, usually fixed meshes, all right, and basically high order methods because they're dealing with basically incompressible fluids, all right? Now, for the GR part, okay, it's probably, moving mesh is probably not the right way to solve GR. And so we are using a mixed grid. We are probably planning on using a mixed grid formalism to do basically GR hydro with full dynamical spacetimes, all right? And the way we're going to do that is basically we're going to use something like a spherical grid or some other grid, basically, on which we will solve the Einstein's equations, all right, and then interface that with the moving mesh part to basically find what the source terms would be in order to plug into the Einstein equations, and then basically from the Einstein mesh, right, basically carry over all the metric terms onto the moving mesh in order to basically solve the GR hydro equations, right? So that's our plan moving forward, all right. So hopefully that answers your question.
Yes, yes, it's a very interesting territory indeed.
Okay, maybe one last question of the morning, Beanie.
Okay, sorry, this was it's kind of trivial, but when you were talking about comparisons, actually the slide you're on right now with the oscillating system and comparison compared to Illinois GRMHD, you were saying one of the differences that inhibits a proper comparison is that the Illinois GRMHD metric is dynamical, but you can freeze the metric in an Einstein toolkit evolution like that. So if you wanted to, you could make it more apples with apples, or apples to apples if you really wanted to.
That's true. So this is so I'm not an expert on Einstein toolkit. So this stuff was done by Zach. I think it's close enough, what we call close enough for government work. But if Zach is around, maybe you could basically elaborate on, I'm sure this is doable, and then we could do the exact comparison then in that case.
Well, actually, it looks like Zach isn't logged in just now. So I'd like to thank all the speakers of the morning, all four. Very good talks, very interesting. As before, thank our technical consultants. And in view of the delay caused by the technical problems, we'll resume at 1:30 and start talking about the conversation for the afternoon.
Thank you.